So in the last video, we had finished making a Turing machine that would solve the palindrome problem for us. And in this video, we're going to kind of continue getting our hands dirty, getting used to Turing machines, but we won't just be doing another example with a single Turing machine. What we'll be doing instead is continuing along and defining multiple string Turing machines, um, and kind of completing the return to the original conception of Turing machines as the natural form of view with graph paper. Because if you have multiple strings, then you essentially do have graph paper in the sense that you have as many rows as you want. And I think through the algorithm that I'll show for just simple addition, I'll be able to convince you that Turing machines are the natural model for computation in the sense that anything that you could think to any algorithm that you know how to do already on the graph on a piece of graph paper, whether it be long division or multiplication or whatever, can be at least conceptually without much uh, thought implemented with a multiple string Turing machine using just whatever number of rows you would need for your normal algorithm. So in any case, what do we mean by multiple string Turing machine? Well, essentially, I mean just multiple rows of graph paper, but let's draw the picture. So right now what I have is like a string of tape, right? It goes infinitely in both directions. But with a multiple string Turing machine, we're of course going to want multiple strings of tape. And we're going to disconnect them. We're going to draw them apart from each other. Maybe I'll put like a dot, dot, dot here to indicate that there could be more than one string or more than three strings, as many as you want. And of course, it goes infinitely far in all these directions. And the reason we want some room in between this, I know this, if you disconnect the tape the tape strings like this, it doesn't really look like graph paper anymore, but we kind of need to in order to indicate with our picture where the cursor is. And this is one part where you might get confused a little bit because you might think that what we want to do is like have a single cursor and have that single cursor bounce around between different strings. And you could do it that way. Um, but that's a little bit confusing because then you would have more than, then you would have essentially 8 or 9 different directions for anything. But I mean, even that wouldn't complicate it that much. But it wouldn't be any worse or better to do what we're going to do. Actually, it probably would be a little bit better. You'll see why it would be a little bit better. But the idea is that instead of having one pencil, we're actually going to have a pencil or a cursor essentially for every single string. Doing this is going to make it seem more naturally like an extension of the old definition, although not as naturally an extension of the original informal idea. But you'll see that through doing this, you get some notions. You immediately get some nice. Uh, it's going to help us talk about parallelism later, and the extent to which parallel computing can help us solve a problem faster or slower. Uh, through defining a multiple string Turing machine like this, I think eventually, probably never in my playlist, but eventually you can start to talk about parallelism as well as just kind of making this the natural extension of a person with graph paper. But in any case, you have multiple cursors in multiple places. Um, and of course, you're looking at a different symbol at each place that your cursor is at. We'll say sigma k, so there's k strings. Um, and basically what's going to happen is the only difference between this and a regular Turing machine is that at every step, all of these are going to be working individually in parallel. So every step, so just like single string Turing machines, I'm going to replace this symbol with something else and move left or right or not move. But that's going to happen to all three of these. So cursors. So it's almost like the idea, I guess you could say, is that it's multiple Turing multiple Turing machines working in parallel. And also uh, multiple rows of graph paper. You can think of it either way. Multiple rows of you know of your graph paper. You can think of it either way. Um, so let's go ahead and just kind of write down the formal definition. The formal definition of a K-string Turing machine isn't going to look much different. I'm only going to write down enough to spot the differences. So a K-string Turing machine is just like before, a triplet. It's a triplet M equals sigma, just like before, Q, just like as before, delta, just like as before. With sigma and Q as before. The only difference is, and by the way, since Q is as before, the idea is that even though we have multiple Turing machines kind of working independently, we do have a single state. So just one state. We don't have a different state for each tape. Is this zoomed out all the way? Oh, it's not. Okay, well, I'll fix that a little later. Okay, so anyway, so these are as before. The only difference is that the function now is a little more complicated. Um, delta is now like this. Delta now takes more inputs, returns more outputs. My definition is going to be a little bit less formal than before. Um, the idea is that, so what does it look like? Let's see. So what do I need in order to get a response from my Turing machine? Well, I need a state, and then I need three symbols, right? So delta is going to take as an input the state, and then each of the three symbols, or each of the k symbols, so sigma 2 dot 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 up to sigma k. So the input is now a k plus one tuple. So it's k plus one inputs, the k symbols plus the state you're in, and then the output is it's going to be a lot of things because it's going to be more because we also need directions. So I'm going to get a q prime. There's going to be a new state, and I'm also going to get a sigma 1 prime, but in addition to the new symbol for the first string, I'm also going to need a direction. So I'm going to label that D1. And I also get a sigma 2 prime, D2, and a sigma 3 prime, D3. So oh, wait. Sorry, I keep thinking I have three strings. I have K. So there's a dot, dot, dot here, and then I have a sigma K prime, DK. So really, it's a pretty messy function. So let's just count. So we've got K. So we've got 2K. Uh, we've got K new symbols, and then K directions, and then one thing. So it's going to be, so the output is actually a 2K plus one tuple. So that's that. What else do I need to say? Uh, um, oh yeah, so technically delta, if you want to write it in the function notation, delta, the big difference in terms of K-string Turing machine versus a regular string Turing machine is that before delta mapped sigma cross q to sigma cross q cross -1, 0, 1. That was our old Turing machine transition function. But the new the K-string Turing machine transition function, we actually have k copies of sigma here as the input, k copies of sigma here as the output, and then also k copies of directions. So we have k uh, k symbols, one state, k, and then as an output, k symbols, k directions, and one state. And of course, these are mixed up, right? I put q here and q here. It doesn't really matter. So that's a K-string Turing machine. We still need to standardize a little bit. So inputs and outputs. I'm going to zoom in a bit, actually. There we go. So as far as inputs and outputs go, the standard will be the input, the initial state looks like this. So we're going to have, our place symbols as before. So there's case there's dot dot dots here. So, but initially I'm going to start off like this. I'm going to start off in my initial QI state, and then the standard is going to be to put the entire input right here in the top string. So this is going to be initial configuration. Input goes at the top string. That's going to be the idea. And then for the output, we still have the same halting states. We still have the same number of halting states. But then also, so basically we'll have stuff in all of the strings except for the bottom one. The bottom is going to be interpreted as the output. So the top string is interpreted as the input in the initial configuration. The bottom string is the output for the final configuration, and will be in some kind of state. It doesn't really matter where any of the cursors are, and then we'll be in some kind of Q halting state. Final config output at bottom string. So that's the idea. So one last thing, let's point out formally what the configurations are going to look like. I know I haven't really used configurations for my original definition of Turing machines. You don't really need them to define programs, but they will be very, very theoretically important. So let's go ahead and just write out what a configuration would look like. So recall for a single string Turing machine, we had, again, I've drawn this picture a bunch of times already, and I will continue to do so. Right, I have some tape, and then I have a location, and then I have a state. So configuration before looked like a tape configuration, a state, and an integer, right? But now the only difference is that we have multiple tapes. We have a K tape Turing machine, so that we're going to have K of these guys, and then of course we're also going to have K of these guys and still one of these guys. So C now, and we're not going to use the same order. It's not super important what the order is at all. But the bottom line is that configurations are of the form C equals, let me put more room. C equals, we're going to have a single state Q. I'll put that first because there's only one of them. T1, T2, dot, 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 TK. And then, of course, Z1, Z2, up to ZK. So that's what a configuration looks like for a K-tape Turing machine. We've got K strings of tape, so K those, and then K integers, and then one state. So that's a K-string Turing machine, just kind of the natural extension of the old definition to multiple tapes. Now we're going to prove that there's no computational improvement in the sense that there's nothing that a regular Turing machine can't do that these can. It's just a matter of efficiency, and what we're going to see is even there, it's very marginal, the extent to which you can improve an algorithm with parallelism of this form. But what we do get is we get a lot of freedom to translate algorithms that you know how to do on paper to Turing machines, and it's in that sense, exactly that sense, that you can that Turing machines are the natural model, and that's important not just to make it natural, but it's important because for your conceptual understanding of just to understand what computation is, we're kind of hearkening to this idea that if you can figure out a standardized kind of algorithm for yourself to do it, it will translate to a Turing machine. And that is something that I need to convince you of before we can get too far into the cool stuff of this theory, is that anything that you can think of an algorithm for, a systematic method of solving a problem, anything that you have an algorithm for is computable and is translatable to this Turing model. So I'm moving around my page. I'm trying to figure out where I want to do the rest of this. But I want to do an example. Uh, Addition. Okay, so addition. How are we going to do that? Well, how do you do it on paper? So if I had graph paper, let's just do 38, 46. How do I do this? I mean, think about this being graph paper. What would I do? Well, I would start here. I would add 8 and 6. I get 14. That's bigger than 10, so I have a carry bit, but I'll put a 4 here, and then I want to keep track of that carry bit. Where's that going? Well, I could put it here, but I could also just keep a mental state, right? That's usually what you do. I'd have a mental state that says that there's a carry bit, and then I'm going to add this normally, but then I'll add one more. So that's the idea. And because we can use as many strings as we want now, or we will be as soon as I prove later that that you can, uh, this the direct translation of this to a 3-tape Turing machine is going to be enough to show that a regular Turing machine can do it. Um, so let's go ahead and just build that. Let's just kind of think about how this would look for a formalized Turing machine, how we can translate this algorithm. So on a 3-tape Turing machine. So let's go ahead and look at it. So initially, we're going to have a state like this. Um, we're going to have, let's say, if I wanted to put this in general, we separate multiple inputs with a blank, with blanks. So I'll put the 38 here, and then I'll put a single blank, and then I'll put a 46. So this is what the initial oops. So this is what the initial input would look like. Since we said that we have to put uh, since we said we had to put everything, since we said the idea is that the input is up here in the top string. So this is probably what the input would look like. I want to add 38 and 46. So of course we would have to, and I'm not going to go over this formally, but we would have to go through a process of, move stuff around. And what I mean by move stuff around is I'm going to move stuff around this way, and I'm just going to do it. I'm just going to skip to this point, and hopefully you can believe me or do it yourself to show that this can be done easily. But what I want to do is it'll start like that, but the Turing machine will initially kind of set itself up to do this addition process by, first of all, putting zeros here, except for here. We're going to put the zeros here. I'm going to leave one bit. So I have a 0 and a 3 and an 8. And again, there's no problem in assuming that that my Turing machine's alphabet is just the digits, right? The alphabet is going to be able to be whatever we want. I still have to prove that that's the case, but we're going to be able to just mix up the alphabet to whatever symbols we care about. So initially, I'm going to move stuff around, and my Turing machine is going to compose itself in this kind of setup, where the cursors are all lined up at the rightmost number, and we've got blanks at the bottom. This is going to be where the output is. And then we just kind of go, and you can imagine how this works. So Q0 will be a state which says, which means no carry bit. And then Q1 indicates a carry bit. So I started with a 38 and a 46 out of here. I kind of set myself up to do the addition. You see I leave some room on the left so that if these two numbers do add up to be bigger than 1, I have room for it here. That's why I did all that. And I won't list every uh, instruction, but I will list enough that you can get an idea of how one would construct this program that does addition in the normal sense. So let's just think about what needs to happen right now. Well, initially, once I'm finished configuring it, I'll start in this state with the with the carry bit, because I don't have a carry bit because I'm all the way on the right. So I'm going to say delta of Q0 because I'm not carrying anything, and I'm looking at an 8 and a 6 and a blank. Right, that's the input at this point. That's what I'm looking at. That's my mental state. And what do I want to happen? Well, I do have a carry bit now because 8 plus 6 is 14. So I'm going to switch into this mental state Q1. I'm going to leave the 8 alone. No reason to change it. I'm going to leave the 6 alone. No reason to change it. But I need to move left in both cases. So I get a -1 here, a 6, and a -1 here. And then I want to put down, of course, a 4. And that would be hardwired into the algorithm. So in a sense, there's no computing what 8 plus 6 is. 8 plus 6 equals 14 is sort of built into this instruction right here. But in that case, what's going to happen is, of course, I'm going to replace this blank with a 4. I'm going to move all of my cursors right. I've got a carry bit now, so I got a Q1, and then this is a 4. And then what's going to happen? Well, I'm going to have, well, now I'm in state Q1. I have a 3 and a 4 and a blank. And of course, that's going to translate to, I don't have a carry bit anymore because 3 plus 4 plus 1 is 8. So I go back to Q0. I leave the 3 alone. I move left once. I leave the 4 alone. I move left. And I replace the thing with an 8. So you can see, I really am not thinking very hard about this at all. My algorithm for addition on graph paper directly, simply translates over here. Now, of course, there's a ton of instructions to write down. To actually program this would be tedious. To actually write down every single instruction would be tedious, but not difficult. It wouldn't be hard. It's very natural. Even here, right now, I'm just in this state, and I would have this hardwired in. Right? The idea is to just keep going until I see play buttons and then halt. So now I'm in Q0. I'm seeing a 0 and a 0 and a blank, and of course 0 plus 0 is 0. I put 0 minus 1, 0 minus 1, and 0. And then finally, the instruction to stop. Well, let me kind of, we'll just keep going one step at a time. And of course, then I stop. So finally, delta of Q0 or Q1, right? I would have to add tons more instructions than this to cover every possible case. These are just the instructions that would be queried, I guess, for this specific instance of 38 plus 46. I'm now seeing a delta and a delta and a delta. And of course, that translates to QH, and then who cares? And so you see, like, this is very natural. If you can do it on graph paper, then you can do it with a KString Turing machine. And in this sense. Um, and so, yeah, I mean, hopefully the naturalness of, I'm not going to do the whole thing, but hopefully this seems natural enough that you're starting to kind of get the sense of how powerful Turing machines are in principle, not in their efficiency to program with, but in their efficiency to directly translate what you think about as computation to this rigor. If you can think of an algorithm, there's a Turing machine for it, and we're going to prove that in more ways than this. Or at least we're going to show that in more ways than this. But hopefully you're getting that sense now. Hopefully you're starting to get that. You're starting to get what I mean when I said natural. Let me do one more thing with K-string Turing machines. Let's improve our, here's another example. Let's improve our palindrome algorithm. With a two-string Turing machine, we can actually come up with a better algorithm for palindrome. How do we do that? Let's see. Um, so the idea is, once again, with two strings. So how would I do that? Well, I'm going to start with something like this. Maybe 0, 1, 1, 0. Let's just stop there. And then initially the bottom one is empty. So I'm going to write this out in steps. I'm not going to write out the program explicitly, but I'm going to say step 1 is copy the top string to the bottom. So I'm going to copy the top string to the bottom. So that we just write the program that would replace all of these with exactly a direct copy of the above. And then move cursor 1 to beginning, wherever it was before. Cursor 2, whoops, to end. And you can already maybe see where this is going. So I'm going to be in the situation where I have cursor 1 up here, cursor 2 down here. And what do I need to do? Move in. Right? Now we can do, think about how many steps the last one took. Let's think about like the original program for directing. We haven't talked about time complexity yet and number of steps. We will soon. But if you think about how long this would take on a single string Turing machine, what do we have to do? We have to look at this and then move all the way over here and then move all the way back and then move all the way over here and then move all the way back. And we have to do that a number of times proportional to how long the string is. So in a sense, if the string, when I put bars around a string, by the way, I'm talking about the length. If the length of the string is, let's say, n, then original algorithm works in time approximately n squared, right? Because I need to go all the way back and forward a number of times, which is equal to the number of characters. So for every character I have to do a number of steps that's proportional to the entire length of the thing. So I end up with a parabolic complexity. I end up with an O of n squared algorithm. What's this though? Well, I have to make a copy of the string. So that's going to take a number of steps that's more or less just equal to the length of the string. So n. And then at that point, I just have to move backwards. And I only have to move like half the length of the string. So basically, the improvement between this algorithm of kind of making a copy and then comparing and moving back, of making a copy and moving back, versus the original algorithm that we wrote down explicitly in the last video, it's an improvement. It's a quadratic improvement from n squared to n in terms of time. So it's a good improvement. However, as we'll see, this is actually the best we can prove. We'll prove soon that this is the best improvement that you can possibly get from any number of strings, in fact. There's a theorem that says that if I have a 12-string Turing machine that does a problem, then there's a single-string Turing machine that does it at the square of that amount of time, no more. If I have it does, like, in other words, the square root improvement is the best that multiple strings can ever do for you. So that's kind of a surprising result. We'll get to that eventually. But this kind of parabolic improvement between a multi-string Turing machine and a single-string Turing machine is as good as it gets. But the fact that there is this direct correspondence, the fact that I can always go from any algorithm like this to any algorithm like this, is going to be very helpful, because it means that if I want to prove things about single-string Turing machines, I can prove things about multi-string Turing machines if it's more convenient, and I still get the results that I was looking for. So multi-string Turing machines are for us mostly an object of convenience, um, but they also sort of serve to help you finish up naturalizing this definition. So hopefully you found that uh, understandable. And in the next video, we will start getting into more theory.